So this is going to be a two-part series on the exchange lemma, the Steinitz Exchange Lemma. The first part will deal with the heuristics. We'll try to motivate the results that we may prove in part 2 formally, and we will try to analyze our motivation, sort of refine it in a way. So let us start by being a little vague. So let us first state the space we are going to work at. So let us say be a vector space over some field F. So essentially we will be dealing with two subsets of V. One will be the spanning subset and one will be the linearly independent subset, so to say. And another one, obviously the linearly independent subset, that is such that L is a linearly independent subset of set, less for future references simply. What I would like to motivate is the fact that the size of the spanning subset will be greater than equal to the size of the linearly independent subset. This should be at least somewhat obviously true. Why? Consider R2. Which can be for a prime, let's not be too formal here, which sort of can be represented like this. Okay, but it can also be represented by adding any other vector from R2, or as many as you like. For our purposes, we will just add one to make a point. Okay. See, if this spans the R2 and this spans the R2, and only difference between two is that this one is a linearly independent subset and this one is not a linearly independent subset because of this vector. So what we can say is linear independence is a stronger condition, so less of the vectors satisfy it. So that kind of says you something about the span of L. It should be sort of smaller in reference to the spanning set. Another argument would be the same, but in a different perspective. That is, if something spans a space, that may not necessarily be the linearly independent set, because this spans R2. This is not a linearly independent set. So it sort of tells you something about the spanning set being larger than the linearly independent subset. You can look at it in both ways. So given that is the point in motivating this is, or giving an obvious why this may be obvious, is the fact that I would like to derive a consequence of it. That is, kind of another thing that I want to motivate. Then suppose this is true, okay, then the point is, can we find some vectors, some vectors of S that when we add them to the vectors in kind of, not really add, but you will see my point, sort of extend, if we could extend the linearly independent subset such that it spans the entire space. That is, So this is our sort of where we are headed to, and obviously we will, if such a thing is possible, then we will have to like find more details about this S prime subset. But this is where the motivation kind of stops and the analysis begins. So now, before we deal in the full-fledged analysis of our motivation or the results we are trying to derive, let us define some things, at least say something about the structure so that we are not too vague. So, as we said before, now let's talk about the structure of S. Obviously, this is straightforward. And something about the linearly independent subset. Such that L is less. Now, as I said before we start the analysis, this at least will state two facts that are very obvious. I will try to at least give some motivation behind them, but anyway, the first fact would be that suppose we have some vector, some LG, and obviously this, and this, if we take it, since this is a linearly independent set, if we take it away from this linearly independent set, then we can no longer generate it by the linear combination of the vectors in plus. What I mean by that is that if this belongs there, then L sub j is not in the span of L, take away the L sub j, because L is less. This is obviously true because that's what the definition of linearly independent subset is. If this was possible, then it was then it is no longer a linearly independent subset. Okay, so another point that I'm trying, technically is the main point that I'm trying to make, is suppose we have this, this spanning set, and we define a different set as follows. Suppose we define S tilde as the original set S, but you take away some vector from it. Suppose we took away Sj. Given that S spans it, let us simply write that if and now is the main thing that I'm trying to say. We have the vector that we took away. Suppose it is in the following span, that is technically not V sub j, but anyway, I want to do this thing. Then should still be the original vector space. But why? Well, see, the only difference between this set and the original S set is that we are missing the S sub j. But if S sub j belongs in this span, then we are no longer missing it. And the original S obviously spans the vector space, so this must also span the vector space. You can prove this on your own. This is not such, it's not an in detail proof or anything. This is an easy one. Okay, let's move on. Okay, so now comes the real analysis part. Okay, let us consider a vector from the linearly independent subset. Let's consider the first vector. So I should say consider one, which obviously belongs to L, which obviously is a subset of E. Okay. Since the vector space spanned by V is spanned by S, that is, since and L1 is obviously contained in V, we should be able to represent L1 as a linear combination of the vectors in S. That is, all these things imply simply that L1 can be written as, let us say, for C sub 1 S sub 1 plus dot dot C sub n S7. This is obviously possible. So now the question that obviously pops up is, can all of the C's be 0? That is, can be equal to the 0 vector of the field? Well, not really. See, if this is the 0 vector, and then L is no longer linearly independent, so this cannot be possible. That is, it's unless this implies that L1 cannot be equal to 0 vector of the field. Well, what is a consequence of this? This implies that there exists at least one C sub j where j belongs to, obviously we are taking natural numbers from 1 to n. J belongs to this. There exists at least one C of j. I should technically say it should be not equal to 0, such that C of j is not equal to 0 of the field. Well, rather than dealing with some C's sub j, we can re-index S and therefore re-index C sub j. That is, re-index S such that S sub j is equal to S sub 1. This implies that, C sub j is equal to C sub 1. Or we could simply say, without a loss of generality, that C sub j is equal to C sub 1. Which is, by the way, again, not equal to 0 of n. So, given that C sub 1 is not equal to 0, we could obviously divide by it and separate our S sub 1. This implies S sub 1 is equal to negative C sub 1 inverse of, it was L1, right? L sub 1 plus C sub 2 F sub 2 plus dot 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 C sub n sub n. Well, what does that tell you about Sn? Because this is a linear combination. This implies that S sub 1 obviously belongs to the span L sub 1, S sub 2, S sub. Since we know something about S, span of S sub 1 comma dot 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 S sub n is equal to the space we are working with, and the only difference between these two sets is that we have replaced S1 by L1, but it contains S2, and as the fact B says, this should also obviously span BFF, which implies span of this set should also be the same. At least it should span the space. Now for future references, we will define the set. Say it's S1 is equal to L sub 1 comma S sub 2 comma dot 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 S sub n. So this subscript representing how many L's are present here, up to which L's. This is where this part ends. We essentially replaced one vector by S. So in order for a more clear picture, let's perform the same action for one more vector so that it's just clear before we can go general. So we have two sets essentially now. That is S1 is equal to and we have our original linearly independent subset. Again, consider this time L2 obviously, which is in the less, which is obviously a subset of V. And we also know something new right now. We know that span of S1 is equal to this, which obviously implies that we can write it as a linear combination of the elements in S1. That is, let us choose something else. Let us choose D, D sub 1, L sub 1, plus D sub 2, S sub 2, plus dot 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 dot. D sub n, S sub n. Now, again, we can ask the same question. Can D sub j equal to 0 of the field for all j's in essentially from here to here, that is to n? Not exactly, because if yes, then L2 is equal to D sub 1 L1. Then this shows linear dependence. This is a contradiction, obviously. This is a contradiction. This cannot happen. So no, because L2 is in less, which implies obviously there exists at least one. This is D sub j not equal to the field of F. For all j's in the same set, there at least one. Again, without a loss of generality, let d sub 2 technically right now, d sub 2, because we want to separate this one, let d sub 2 not equal to the 0 of the field. Then we can essentially divide by it and separate our S2, which will be done in the next slide, obviously. And S2 is equal to what? We will have, so how is it? Sure. Will be equal to negative d sub 2 inverse of, first of all we will have d sub 1 L sub 1, and we'll have a negative L sub 2, and afterwards we can simply have L sub 3, d sub 3, S sub 3, plus dot 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 till n. Which says something, since this is a linear combination, it says something about S2. Span of L sub 1, L sub 2, sorry, S sub 3, comma, dot 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 S sub n. And since we know something about the previous S statement, that is span of L sub 1, comma, S sub 2, comma, dot 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 sub n spans the vector space. And only difference between this and this is of S sub 2, and it contains S sub 2. This simply spans the this original vector space that we're working with by the fact 2, obviously. Okay, this, by the way, would be what? This would be S2, because this one is replaced by the S. So this is the, I hope you have got the hang of it, so we can kind of generalize it in a sense. So now we will try to make an attempt at generalization. After, see, if we follow this process, after the m-1 iteration, iterations, after m-1 iteration, we will have the S of m-1 equal to, under a condition that we will discuss later on, will be equal to obviously S1 dot 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 S m-1. Then the then comes the S vectors, that is m comma dot 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 up to n. And the condition, obviously, as it's as I wrote it out, is that n is greater than or equal to m, which is same as saying, you know, that the size of x is greater than or equal to both sides of that. Now, yes, we are sort of assuming it here, but we will give a justification later on why it is true. And in the second part, this will be a natural consequence of our proof. We won't have to like tug around with it. So if after m-1 iterations, obviously this will be the S of m-1. Now, again, let's play the same game. Consider m which belongs to S, which is a subset of V. We will have that something spans again, span of S sub M minus 1 using the same set of rules. We will have that this will be equal to the same original vector space, which would imply we should be able to write this as a linear combination of the elements here. Well, we were on D, yeah. Let's use A. A sub 1 L sub 1 plus dot 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 plus A sub M minus 1 L sub M minus 1 plus dot 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 plus S sub D A sub M plus dot dot dot. This goes all the way. Oh, my bad. Just dot 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 here. Kind of hard to do. And all these vectors are in. And I have to A sub N S sub M. Okay, this should be possible, obviously. And we can ask the same question again. That is, can A sub J equal to B0 of the field for ours J is N. Now we will be looking from here to here. That is N of N. Well, not exactly. Suppose this is true. Then L sub M would be equal to this guy. Which is a contradiction because L is a linearly subset, and we cannot obviously write this in terms of others. This is a concept, so we can just say no, because L sort of, let us be more clear, L sub M belongs to less. Okay, done with that. Then now this gives us a freedom that here exists. At least one A sub J not equal to the 0 of the field. For all G. At least one. Again, we will use the same trick, that is without a loss of generality. Let right now we have to keep it to the m's, that is let A sub J equal to the A sub M, obviously. A sub M we belong to 0. If that is true, we can obviously isolate S sub n by dividing by this. Okay, let me just try to do it on my own here. So we will have S sub m equal to L sub negative, that would be negative, so this would be, we were following the convention, so negative A sub m inverse, and we will have A sub 1 L sub 1 plus dot 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 minus L sub m, right? And we will have plus m plus 1, right? A sub m plus 1 S of m plus 1 plus dot 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 plus A sub m S sub n. which obviously implies that belongs in the span. Okay, here we can sort of define some things. This is obviously the orthogonal linearly independent subset. This is a subset of the orthogonal S. Let us call this S prime simply. That is, S prime we defined as okay. So this implies that S sub m belongs to the span of L union S prime. Since let us say, since span of S sub m minus 1 is equal to B, and the only difference between this and this is of S sub m, and it contains S sub m, then this should also span the same space, which implies that the span of n union S prime is equal to V of n. This is sort of one of the results that we wanted to prove. One was obviously that the size of S is always greater than or equal to the size of M, which we have not proved exactly. We have assumed it. We will give a justification later on. For now, we got something like we got a structure of S prime. Let us try to see the cardinality of such a set. That is, consider S prime. That's what is this equal to? Essentially, it's we are skipping one ahead, so it's n minus n, because we are skipping one ahead, which is same as the span of S minus the cardinality of S minus the cardinality of N. So this tells you something about the cardinality of S prime being the difference of these two sets. That should be interesting, or at least in the formalism part we can include that part. So let us justify the fact that this is greater than or equal to this, or to speak in terms of the structure. See, let us consider the set that we are left after the m iteration, that is sub m, which would be obviously equal to n sub 1 comma dot 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 n sub n comma s sub m plus 1 comma dot 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 s sub n. Now we will assume the contradiction of this. That is, suppose that then obviously if n is less than or equal to m, there won't be any s's more than there won't be any elements with index more than this. That is, how should I say it? I should say s sub I for I greater than m do not exist, which would imply that s sub m is equal to l sub 1 comma dot 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 l sub n, which is just l. Now, if s sub m is l, and we know something about this s sub m, that span of S sub m is equal to V of F. Then any L sub J, which would be an L which is a subset of V, can be written in the linear combination of the elements of this. Can be represented as let me just write it here. Some ABC. Yeah, let us tell you, see C sub M technically, and S sub N. This obviously is a contradiction because L is in less. So no, because L sub J belongs to a linearly independent set, which obviously implies that S should be greater than or equal to F, or N should be greater than or equal to M. So what is the conclusion? The conclusion of our analysis is that let us write it all down. Let V form a vector space over F. Let S of the form of this such that and L sub M. The conclusion is as follows. If L is a linearly independent subset or linearly independent set, then we can say the following two things. That is that cardinality of the size of S is greater than or equal to the size of L. This is equivalently saying this. And the second part, which is crucial enough, that is this is S prime, this is a subset of S. That's a subset of S with the size of it being the difference of two, such that it also, the union of it and the linearly independent set can be extended by it to span the original subset, such that S prime. So this is a result that our heuristics have got us to. Now the point of next video would be to assume this, state this as a lemma and then try to prove it on our own. Obviously this was a constructive approach to it, and now we will just try to take an inductive approach to it. That's all for this video.